Uh, uh, Hello everyone. Today, a team consisting of Adarsh, Sneha, Abhijit, and myself, Hardik, will be presenting a very recent paper by Lualdi et al. About fast quantum interferometry at the nanometer and attosecond scale with high energy entangled photons. We will be walking you through the physical limitations of current interferometry techniques, the mathematical framework of the researchers' proposed solution, and how they applied it experimentally. Okay, to start, let's look at the core problem the researchers set out to solve. In classical optical interferometry, signal loss and background noise make it incredibly difficult to achieve fast nanometer resolution measurements when working at low light levels. Quantum two photon interference offers a theoretical way around this, as it is completely unaffected by background noises. However, it actually making nanometer scale resolution with standard quantum method is a physically demanding and a tedious process. As a solution, the authors of this paper enhances two photon interference using highly non-degenerate energy entanglement. Specifically, the result of this modification is highly practical. They achieved measurement resolution of the nanometer and attosecond scale using only an on the order of 10 to the power 4 photon pairs. Doing it despite the presence of background noises and losses. To validate their instrument, they performed a non-destructive contactless thickness measurement of a metallic thin film in matter of seconds, successfully matching the resolution of atomic force microscopy with which often requires destructive measures. Okay, let's step back and review how classical optical interference operates. An electromagnetic wave travels in a superposition of two paths. It then recombines on a balanced beam splitter where it either constructively or destructively interferes with itself depending on the relative phase between the two paths. This mechanism has diverse applications ranging from gravitational wave detection to long base astronomy and optical coherence tomography. But it has a strict limitation. If you look at the first set of graph on the slide, you can see the issue clearly. The graph on the left shows a balanced system. It produces a clean signal with high interference visibility, yielding high resolution. The graph on the right shows what happens when we introduce imbalance, path, and optical background noise. The signal is reduced and the visibility is compromised, and the attainable resolution drops significantly. To operate in these noisy environments, physicists use quantum interference. This process involves two photon incidents on the two inputs of a balanced beam splitter When these photons are non-distinguishable, meaning they arrive at the same exact time, their bosonic nature forces them to always exit the beam splitter in the same port. Sorry. The second diagram on the slide illustrates why this is so valuable. It compares the classical setup on the left with the quantum setup on the right. While the classical interference signal gets scrambled by noise and attuned photons, the visibility of the two photon quantum interference remain inherently robust against the imbalanced path loss and optical background. But standard quantum interference has one catch. When two photons bunch together and exit the same spot, it creates a dip. In the probability of them exiting separately, the attainable measurement resolution is determined by the width of that dip, which is inversely related to the photon bandwidth. This achieving nanometer resolution traditionally required either hour-long measurements or the use of uh, ultra broadband photons, which eventually destroys the surface. The author solved this by using energy-entangled photons. In this state, the traditional interference dip is modulated sinusoidally. The period of this modulated uh, modulation varies inversely with the difference or the beat note, which is between the frequency of the entangled photons. This gives us interference fringes of a similar pattern as in classical interference, but with photon protection. Ultimately, this scheme increases the information acquired per photon pair and saturates the quantum Kramer-Rao bond, meaning it hits the mathematical limit for maximum measurement precision. Achieved, we need to look at the mathematical framework of how these states propagate under two photon interference. We begin by describing a single photon with a finite spectral bandwidth phi and the integral f omega 1 describes the frequency spread of the photon, which we mathematically modeled with a Gaussian distribution, as you can see on the right. The creation operator A dagger omega 1 then acts on the vacuum state to create the photon. Once we establish that, we can easily generalize it to a pure two photon state. In this two photon expression, the function f omega 1 omega 2 is critical because it captures the spectral information of both photons combined. This includes any potential frequency entanglement between them. We then apply two creation operators A1 dagger and A2 dagger, which represent the photon in spatial mode 1 and 2 respectively. Next, we introduce the 50-50 beam splitter into the system. Whenever two photons are incident on the beam splitter, their spatial modes mix. Mathematically, this means our creation operators undergoes a transformation. The operator for the first port A1 dagger transforms into 1 over root 2 A1 dagger plus iota A2 dagger. Similarly, the operator for the second port A2 dagger transforms into 1 upon root 2 A2 dagger plus I A1 dagger. The crucial step in this derivation is analyzing what happens to the product of these two operators A1 dagger, A2 dagger after passing through the beam splitter. When we substitute the transformed operator back into our product and expand the expression, we get an equation containing four distinct terms, two real terms and two imaginary terms. It is important to understand what these terms represent physically. The two real terms contain combination of A1 dagger, A2 dagger and A2 dagger, A1 dagger. This corresponds to a state where one photon emerges at port 1 and the other photon emerges at port 2, as you can see in the diagram. In an experiment setup, this triggers a click at both detectors simultaneously, and this is what we call a coincidence. The two imaginary terms, however, A1 dagger, and A2 dagger, A2 dagger, physically represent both photons have bunched together and exited the beam splitter entirely out of port 1 or entirely out of port 2. In this scenario, only one detector clicks. This is anti-coincidence. Because because measurement schemes relies entirely on extracting the coincident probability, we are only interested in the events when the photons split between the two parts. Therefore, we deliberately discard the imaginary anti-coincidence terms. This gives us a simplified final expression for the beam splitter's action, clearly setting up the math we need to calculate our final measurement resolution. Now I will hand it over.
So far, we have seen how the two photon state can be represented mathematically using A dagger operators acting on vacuum and what happens to it once it passes through the quantum beam splitter. Now, we introduce a delay in spatial mode A1 through a term e raised to I omega 1 tau, where tau represent the relative temporal delay. Now, when it is passed through a beam splitter, that is a 50-50 beam splitter, we have this expression as the state of the system. So we have f of omega 1 omega 2, the spectral information term, then the term corresponding to the delay in spatial mode, and these two terms which correspond to the coincidence term as a result of the beam splitter. So as we notice here, there are only two terms present, that is the terms that is corresponding to the coincidence in which two the photons, each of the photons emerge at different ports. A1 dagger, A2 dagger here, A1 dagger here, A2 dagger here. There are no terms that correspond to the anti-coincidence. That is, these two terms are not present. So this is what happens once it passes through the beam splitter. Now, the next part after the beam splitter is the detection of the photons. So we detect using a pair of detector with a flat frequency response given by this operator denoted by this mathematical expression, that is S operator, which is represented as the outer product. So To determine the probability of coincidence, we take the expectation value of this particular operator, that is S. So once we do the mathematical steps by substituting the value of psi tau is nothing but this mathematical state. Once we substitute this and we do the mathematical simplifications, we have this expression, that is the probability of coincidence PC is given by half of f of omega 1 omega 2 mod square integrated over d omega 1 d omega 2 minus the second term, that is f of omega 1 omega 2 f star of omega 2 omega 1. Then there is the the relative frequency difference term, e raised to I omega 1 omega 2 tau. This term is important. So the second term is more important because the first term uh, can be simplified using the normalization condition. So if we have a close look here, this term is nothing but the normalized term. That means this can be simplified to 1 by 2. So in the second term is what is more important. So as we can see here, there is a relative frequency. The detuning term is present here. So this is very important. Till this point, we have seen how an idealized two-photon state with a temporal delay was sent to a beam splitter and eventually detected. Now we move on to a more realistic experimental setting where a pair of photons produced by continuous wave spontaneous parametric down conversion with pump frequency omega p is the sum of the frequencies omega 1 and omega 2. So this system is described by the state psi SPDC and its mathematical form is given in the slide in this expression. So as we can see, this is very similar to our idealized case in which our state looked like this, and the f was given in the Gaussian form through this expression, in which sigma was the photon's half bandwidth and omega 1 0 was the central frequency. So we have our mathematical form of the state in this format, and the A1 diagram and A2 diagram are acting on the vacuum state. So if we compare this expression with our idealist case, the FSPDC, that is a spectral information term, the coefficient FSPDC omega 1 omega 2 is of this format. That is, we have the 1 by 2 pi sigma square raised to 1 by 4 term here and the exponential term here, and we have two delta function also. This delta of omega 1 minus omega 1 0 plus omega 2 omega minus omega 2 0. Omega 1 0 and omega 2 0 are the central frequencies. So once we substitute this frequency spectrum in the expression that we obtain for probability of coincidence, we obtain this expression as our probability of coincidence for the pair of photons by continuous waves spontaneous parametric down conversion case. So we have PC equal to 1 by 2 times 1 minus beta e raised to minus 2 sigma square tau square. So where beta is exponential minus delta omega square. So delta omega square is the detuning between the frequency divided by 8 sigma square. Sigma square is the bandwidth of the photon's angular frequency bandwidth. So beta e raised to minus 2 sigma square delta square. So we have this exponential decaying term here over here. Now we consider the energy entanglement part, which is crucial for the experiment and which gives us unique expressions. So if energy entangled photons are used, we have two terms in the frequency spectrum, that is this frequency spectrum, which is FSPDC omega 1 omega 2 plus FSPDC omega 2 omega 1, and we have this additional 1 by root 1 plus beta term also here. And once we substitute this frequency spectrum, spectral information part in our original expression for probability of coincidence, we obtain, in addition to these two terms, that is 1 and minus beta, this exponentially decaying term, cos delta omega tau times e raised to minus 2 sigma square tau square. So this additional term appears in addition to the other two terms. And by our choice of parameters, we usually take, in this expression, in this experiment, we take delta omega to be 177 gigahertz. And if we take sigma around gigahertz, we can take the limit beta tends to 0. So in this case, probability of coincidence, PC becomes 1 by 2, 1 minus cos delta omega tau, e raised to minus 2 sigma square tau square. So this cos delta omega tau, this is the reason we are able to achieve the nanometer resolution. So we will be moving to that next. So we have the final expression here, and we in this part have plotted the coincidence probability PC of tau against the path delay, that is tau. So before that, our energy entangled state need not be completely pure. So in the experiment we are doing, we have around 89% purity, and for such purity given by epsilon, we have this correction of epsilon in to our original PC expression, and this has to be incorporated for our results. So for 89% purity and our delta omega at 177 gigahertz and sigma at gigahertz, we have plotted coincidence probability versus path delay. So as we can see, the cosine term is dominating and the exponential term doesn't come into picture. So the coincidence probability PC is rapidly oscillating. This is different from Hongo dip when there is a single dip is observed. So in that case, the coincidence probability PC is not rapidly oscillating, and thus we can't detect the path delay for small path delay for changes in PC. And that is the importance of this cos term. So now I will explain how this nanometer resolution is achieved using this. So the energy entanglement results in this rapid oscillation over the single dip case due to the presence of cos delta omega tau tau. And now this rapid oscillations correspond to large slope, that is maximum dpc or maximum dpc by d tau. So this dpc d tau being very high correspond to increased sensitivity of the relative temporal delay tau. That is, even for small tau change, we can detect large change in PC. Thus, we have a good sensing mechanism for temporal delay tau, and temporal delay corresponds to our nanometer scale resolution. That is, small temporal delay can be detected and nanometer scale resolution can be achieved. So this is concludes the theory part. And before going to the experimental setup, we need to be also aware about the quantum Fisher information, which is important for a given measurement of parameter tau using this quantum state psi tau. Resolution measurement psi tau is given by Quantum-Kramer-Rao bound. So this Quantum-Kramer-Rao bound is proportional to the square root of n, which is the total number of trial measurement, and q, which is the quantum Fisher information. So quantum Fisher information is given by this particular expression for a given psi of tau. So in our case, for our psi of tau, which is given by this particular uh, state, psi of tau, we have obtained the quantum Fisher information as delta omega square, which is the detuning part, and plus 4 sigma square. Sigma square is the half bandwidth part. So this quantum Fisher information has to be very high so that we can achieve high nanoscale resolution.
So, having covered the theoretical foundation in the earlier slides, let me now walk you through how the authors actually built and operated this quantum interferometer. This is where the physics gets translated into engineering and is quite elegant. The experimental setup is the bridge between the mathematical framework that we have discussed and striking results that we will see shortly. Here is the experimental apparatus taken from the paper. At first, it looks very complicated, but it becomes very clear once you break it into three functional modules which are color coded in the original figure. The purple region on the left is the source module. This is where entangled photon pairs are generated. The green region in the center is the interferometer module where the quantum magic happens, where polarization entanglement is converted into energy entanglement, and the photons are made to interfere. And the blue region on the right is the detection module, where the photons are sorted, detected, and counted. Everything in the experiment flows from left to right through these three modules. Let me go through each one in detail. So before we go into in detail for the three modules, let us now look at this interactive animated video. Take a moment to note the scale of the setup. This is a tabletop experiment built on a standard floating optics table, fully enclosed to minimize air currents. Despite its compactness, it achieves resolutions that were previously possible only with long hours integration on large instruments. Here you can see whatever is happening in all of the three modules. Okay. So let's look at the three modules in summary before diving deeper. Module 1, the source. A 532 nanometer continuous wave laser pumps into MgO-PPLN crystals via spontaneous parametric down conversion or SPDC. This produces highly non-degenerate photon pairs, one photon at 110 nanometer and another at 1550 nanometer. The source is extremely bright, over 10 to the power 5 detected pairs per second per milliwatt of pump power. That's a critical number. It's what allows the system to achieve nanometer resolution in just seconds rather than hours. Now the interferometer module. This is where the polarization entanglement is converted into energy entanglement. The two photons modes are interfering on a 50-50 beam splitter and the key tunable parameter is the path delay tau, controlled by an optical trombone stage. The frequency detuning between the entangled photon is delta omega and 2 pi into 177 tetrahertz. As you see in the theory, this enormous detuning is what produces the fast oscillating interferer fringes that gives nanometer scale resolution. Now the module 3, that is the detection module. Superconducting nanowire single photon detectors or SNSPDS detects the photons with extremely low time jitter. A time tagger records four coincidence channels simultaneously. Monitoring all four channels allows the normalized coincidence probability PC to be extracted directly without needing to characterize system losses, a very significant practical simplification. Now let's look more carefully at the source. Generating high quality, highly non-degenerate entangled pairs is non-trivial. Step 1. The pump. A 532 nanometer continuous wave laser beam is incident on a pair of calcite beam displacers. The beam displacers laterally separate the horizontally and vertically polarized components of the beam into two parallel beams, each carrying one polarization. The SPDC crystals. Step 2. Each polarization component pumps its own MgO PPLN crystal. These are 20 millimeter long crystals with a 7.4 micrometer polling period designed for type O phase matching, meaning ordinary polarized pump photons produced ordinary polarized signal and idler photons. One of the two crystals is rotated 90-degree about the optical axis, so its output pairs are orthogonally polarized related to the first crystal's output. Step 3. Because both the crystals are equally spatially recombined by second set of beam displacers, the resulting state is a coherent superposition. Either the H-polarized form produces H-H pair at 1550 nanometer and 810 nanometer, or the V-polarized form pair produces a V-V pair. This gives us polarization entanglement state. The quality of this state is confirmed by quantum state tomography, purity of 90.3, concurrence of 89.6, and the entangled singlet fraction of 94.8. These are excellent numbers, confirming near maximum polarization entanglement at the interferometer input. The key takeaway from the source module: a very bright, high purity, polarization entangled source of photons at two very different wavelengths, 810 nanometer and 1550 nanometer, separated in frequency by 1177 terahertz. This slide covers the most important concept, that is converting polarization entanglement into the energy entanglement. Here's how it works. The polarization entangled state enters into the interferometer module. It passes through the polarizing beam splitter or PBS. The polarizing beam splitter transmits H polarized photons into spatial mode A and reflects V polarized photons into spatial mode B. Because the two wavelengths in our entangled state correspond to orthogonal polarizations, the PBS effectively routes the 1550 nanometer photon into one spatial mode and 810 nanometer photon into the other. A half-wave plate in mode B converts the polarization from V to H, making the photons in both modes identical in polarization. The result is the energy entangled state, a superposition of 1550 nanometer in mode A and 810 nanometer in mode B and 110 nanometer in mode A and 1550 nanometer mode B. This is exactly the probe state from the theory from the paper. These energy entangled photons then impinge on 50-50 beam splitter and interfere. The relative path delay tau between the two modes is set by an optical trombone, a retroreflector on a piezoelectric nanopositioning stage. This gives nanometer resolution in delay over centimeters of travel, which is important for the dynamic range of the measurement. The observed interference fringes oscillate sinusoidally with a period of 1706 nanometers, precisely what you would expect from a frequency difference of 177 terahertz. The fitted fringe visibility is 88.9%, very close to 87.4%, which is expected from the state purity, and the optical component imperfections. Importantly, the individual detector fringes show less than 1% visibility, confirming that it is a two-photon interference, not single photon interference, that dominates. Once the photons exit the beam splitter, the detection module takes over. At each of the two output ports A and B, a dichroic mirror separates the 110 nanometer and the 1150 nanometer photons for coupling into individual single mode fibers, leading to SNS PDAs. The superconducting nanowire single photon detectors, which have a time jitter of around 75 picoseconds. These give four coincidence channels, namely 1150A and 810B and 1150B and 810A are the coincidence channels where the photons exist in opposite ports, and 1150A and 810A and 1150B and 810B are the anti-coincidence channels where the photons exit the same port. The normalized coincidence probability (PC) is then measured directly as a ratio of coincidence events to total events. This is a major advantage over prior approaches that required either extensive loss calibration or probabilistic detector tests. Here, everything is directly measured. The coincidence to accidental ratio is approximately 1100, confirming that the accidentals are essentially negligible. And the plus minus 50-second picosecond coincidence window combined with the narrowband photons suppress the per second background rate by 100 decimal. This is the quantitative basis for the remarkable background immunity we will discuss next. With 59,000 total coincidence detections in 1 second at 1 megawatt 1 milliwatt power pump power, the achieved resolution is 1.26 nanometers spatially, or equivalent to 4.2 attoseconds, representing 88.88% saturation of the quantum Kramer-Rao bond. Now that we have discussed through how the apparatus works, let's turn to the results and what they mean. The discussion section of the paper is where the authors place their results in the broader context of quantum metrology and highlight the genuine advantages of the energy entanglement approach. The comparison table on the slide captures the central achievement of the paper. Let me walk you through it. Prior state of the art in conventional, that is non-ultra broadband quantum interferometry was demonstrated by Lyons et al. In 2018. They achieved attosecond scale resolution, but it required on the order of 10 to the power 11 photon pairs and hours of measurement time. Broadband 2 photon interferometry can achieve submicron to nanometer resolution but requires ultra broadband photon sources that span 177 terahertz in bandwidth. Such sources are technically very challenging to build, and optical systems that support such bandwidth are difficult to realize. This work, the authors have achieved 1.26 nanometer resolution equivalent to 4.2 attoseconds, usually only on the order of 10 to the power 4 photon pairs, completing each measurement in 1 second. That is a reduction of 7 orders of magnitude in required photon number, achieved by using large frequency tuning of the energy entangled state rather than the broadband bandwidth. Figure 2 shown here validates this with 100 repeated trials at multiple set displacements. The measured displacements track the set values accurately from sub-nanometer through hundreds of nanometers, with error bars consistent with the theory. Figure 3 shows how resolution scales with integration time, and crucially, figure 3b shows the experiment result sitting near the quantum Kramer-Rao bound at 90.3 state purity. The system is operating close to the fundamental precision limit allowed by quantum mechanics. This is the headline result: fast, near optimal quantum measurement at nanometer precision with a photon budget that is practical for the real world applications.
So at this point in the presentation, we understood how the interferometer is built and why energy entanglement give us the superior resolution. But a crucial point remains: how does the system actually perform in the real world conditions? The real world conditions are messy. There are many things which can alter. So there are many things which can alter our experiment. You have optical loss, stray loss, background loss. So let's talk about the robustness of our system. The author tested two types of the adversarial condition: imbalance in path loss and optical background. So first we go with the path loss. Imagine you insert a attenuation element in one of the two interferometer arm, let's say in second arm. In classical interferometer, this immediately disrupts the photon superposition state. The visibility starts dropping right away, and by that time you have lost about 10 dB. That's about 90% of the your light. The classical visibility was have already halved. Now look at what happened in the quantum state. Because two of the photon interference in is a joint two photon process, loss in one arm simply reduces the rate at which the coincidences have detected. It acts as a global factor on the quantum state. Sorry. The shape of interference fringes and therefore the visibility is unaffected. In fact, quantum visibility stays robust all the way up to the 20 dBs of loss with a extraordinary. This is extraordinary. The slight degradation beyond that is explained by noise photons. from the experimental imperfections, and the other noise adjusted theoretical model tracked the data closely. Now, for the second test, which is optimal background, the researchers literally shown a halogen lamp at their apparatus and the progressively ranked it up. Even when the background photon made up 100% of the individual detector clicks, the quantum interference visibility was completely unchanged. So, how this is happening? The key is coincidence detection window. The background photon are random and uncorrelated in time. For a background photon to register as a uh, accidental coincidence, it would it it would need to arrive within a 50 picosecond of a genuine signal photon. Combined within low jitter superconducting detector and the narrow spectral bandwidth of the entangled photon, which in contrast the exact same uh, sorry, which allow tight spectral fitting. This surpasses the background by a staggering 100 dB. In contrast, the exact same background caused a 97% visibility reduction. In classical interference, the classical interferometry simply cannot discriminate signal from the noise in this way. This slide really shows why quantum two photon interference is not just a laboratory curiosity. It is a fundamental better suited for lossy and noisy real world methodology. So now this is our next slide, and which is methodological study nickel, which is nickel thin film. So now let's see this capability in action with real world practical measurement. The author measured the thickness of a nickel thin film deposit on a sapphire wafer, a genuinely challenging target because the nickel is a lossy material. It absorbs and attenuates light, which is exactly the kind of the sample that trips classical optical methods. Here the experimental setup, the sapphire wafer is placed in mode B of the interferometer and the scanned transversely across the beam, moving from an uncoated region to the nickel coated region. The optical beam has a mean diameter of 1.2 mm. They run 100 tides per position with a 1 second integration time and monitor how the coincidence probability changes at the as the sample move across the edge. The result from the quantum interferometer, a film thickness of 7 in error of plus minus 1 nanometer. A film thickness is 7 nanometer, and the error of in the thickness is 1 nanometer. This agree beautifully with the atomic force microscopy, which gave 7.4 uh, nanometer, and the error is 0.01 nanometer. Now here's the critical comparison. The classical interferometry used the same apparatus but with classical 1550 nanometer light return a thickness of 9 nanometers, a completely unphysical negative result. The lossy nickel film degrades the fringe visibility so severely that 95.7% down to 82.7%, that the phase measurement between became corrupted. The phase measurement became corrupted. The film appeared as a edged substrate rather than a deposit coating. The quantum fringes, in contrast, are essentially unchanged by the film's losses. Visibility barely moved from 88.5% to 88.2%. This is very less. There is also an important advantage compared to other techniques. Atomic force microscopy, while accurate, was destructive in this case. The researchers had to physically remove a small patch of a nickel with the AFM trip, just expose the substrate for a reference measurement. Scanning, stylus interferometry, and 3D optical interferometry both have limitations in accuracy or resolution. The quantum interferometer was contactless, non-destructive, and correct. So these things have better enormous practical use. And now we will head back to next slide, which is graphical analysis of the results. Now this slide shows us the experimental data from the thin film measurement. Let's talk about what we are seeing. The top panel shows the coincidence detection rate as a function of small position. Notice how you can notice how the count rate drops significantly as the beam crosses into the nickel coated region from around 1200 pairs per second on coated region down to about 68,000 on the coated region. This confirms a roughly 47% transmission throughout the quantum probe. Consistent with the nickel's optical observation, the transition is sharp with resolved, sharp and well resolved. The bottom panel is where the key comparison is mode. It shows the interferometer displayed, the measured path length change, and a function of sample position. For both quantum and classical interferences, the quantum data traces a clean step like. You can see that this clean step like character. So, one transition from zero displacement to approximately 7 nanometers as the beam crosses the film edge. The fit to the theoretical model, a Gaussian probe scanning over a sharp step, is excellent. The classical data shown alongside tell us the dramatically different story. Instead of showing a positive displacement corresponding to an added film layer, the corresponding curve returns a negative displacement. The lossy film not only reduces the classical fringe visibility but also corrupt the phase measurement, leading to a completely wrong physical interpretation. The error bars in the quantum data are larger in the coated region, partially because the reduced photon count lowered the statistical prediction, and partially from the slow phase drift during the scan. But crucially, the measurement is still accurate, and the theoretical error bars assuming no drift, confirming the quantum system is performing close in the fundamental limit. Now we go to next slide, and which is this, which is mathematical framework of the quantum beat node. Let me now bring the mathematics together in to show why this system achieved the resolution it does and why the 177 terahertz detuning is the key factor. The probe state is an energy entangled two photon state, a superposition where the photon are at frequency omega 1 is in mode while photon 2 is at omega 2 at mode B, vice versa. When this photon impinge on a 50-50 beam in splitter, the coincidence probability is written by this formula. Where the del omega is frequency detuning equal to 2 pi times the 177 terahertz experiment, and tau is the relatively temporal delay between two paths. The cosine term, which creates the fast oscillating sinusoidal fringes, the period of these fringes is 2 pi by del omega, which work out about the 1706 nanometer, is exactly What was measured experimentally? The exponential envelope term, controlled by the photon bandwidth sigma, uh, sets the overall window over, over which fringes are visible. Because the photon have a nanoband, this envelope is very wide, about zero point 0.7 millimeters. This is a huge practical advantage. It is easy to find the fringe region during the alignment, unlike the ultra broadband approach where the fringe envelope is only a few hundreds nanometer wide. Now for the precision, the quantum Kramer-Rao bound tell us about the minimum achievement timing resolution, which is this formula. At 177 terahertz detuning, the dominant term in the del omega square, more detuning means better resolution, and that is entire philosophy of this paper. Rather than increasing the photon bandwidth or the measurement time, they engineered a large frequency separation with 59,000 detected pairs in 1 second. They achieved a resolution of 1.26 nanometer, which represent 88% of the quantum Kramer-Rao bound, remarkably close to the theoretical maximum. Now we go to the next slide, which is the limitations and constraint of our experiment. No experimental result has complete without an honest discussion on the limitation, and the authors are admiring candid here. Here are three main constraints about the understanding. First, stability. The interferometer currently relies on the passive stabilization only. It's enclosed in a plastic housing of reduced air currents and uses thermally compensated mount, but there is no active phase locking. As a result, the interferometer phase drifted at roughly 1 degree per minute. This limits useful integration times at around one of a few seconds. Extending the 10-second actually worsen the resolution from a predicted zero point 0.4 nanometer to measured 2.7 nanometer, because drift accumulate faster than the signal improves. The good news is that because nanometer resolution is achievable in 1 second, many measurements can be made quickly enough that drift is large irrelevant. Second is dimensionality. The current apparatus perform one-dimensional scan. Full 2D surface topography could require raster scanning or a detector array. The authors note that a straightforward and engineering extension that has already been demonstrated in the related energy entangled interferometry work. Third, throughput, which is fourth order pairs per second, is efficient by quantum optics standard. It is orders in the magnitude fewer photon than a classical laser. For applications required ultra-fast dynamics, imaging something that changes in microsecond, this remains a limitation. But for many metrological contexts, especially those involving the fragile or photosensitive sample, this low light operation is actually a feature, not a bug. These are real constraints, but they are engineering challenges, not fundamental physical barriers. Now, next is the future works toward bioimaging and advanced modes. Looking ahead, the author sketched several exciting directions of this technology. The most compelling application is quantum optical coherence tomography, or QOCT. Classical QOCT is quite widely used in the ortho orthotology and cardiology to image tissue at the micrometer resolution. A quantum version, leveraging the same energy entangled pair, could push axial resolution to the nanometer scale. The system's impurity to loss, up to 20 dB, and its massive background suppression make it particularly suited for the turbid scattering media like biological tissue, skin, and fog, which is OCT struggles. On the instrumental side, the most impactful near-term upgrading would be the active phase locking. Adding a feedback servo to stabilize the interferometer phase would push resolution toward the picosecond scale, well beyond the what passive stability allows, while also enabling much longer integration times. The apparatus also support two additional operating modes, not demonstrating the main result. This first use not emergent, non-degenerate photon pairs to observe the beating between the 1500 nanometer and 810 nanometer signal fringes. A different regime of the classical quantum interference. The second replaced the energy entangled state with a frequency dependent non-state NOON state, where the interference period is set by the sum of the two fringes rather than the difference, giving a 532 nanometer fringe period. This opened the door for probing the sample that are opaque at 932 but the transparent at 810 and 550 nanometers. And our next is conclusion. So let me bring this all together. This paper represents a genuine breakthrough in the quantum metrology by combining highly non-degenerate energy entanglement with the photon separated at the 177 terahertz with conventional two-photon Hong-O model interference. The author have demonstrated a system through a simultaneously achieve what previous thought of required to trade off, just like precision, 1.26 nanometer resolution, eventually 4.2 attosecond achieved in just 1 second of the measurement time, with only around 10,000 to 60,000 detected photon pair work needed hours to and 10 to the power 11 photons for comparable resolution. The robustness, full interference visibility maintained even at the 100% optical background and up to 20 dB of the imbalance path loss. Condition that completely destroy our. These are the conditions which completely destroy our interferences. And second is robustness, full interference visibility maintained even with the 100% optical background and up and further. Then is utility. This is a niche optical quantum optics demonstration. It is a platform for the quantum sensing in conditions where the existing technique fail. Lossy sample, scattering media, photosensitive biological material with active stabilization and 2D scanning approach could enable the quantum imaging capabilities that classical optics simply cannot match. And this is my conclusion. And our last slide is thank you.